Are these the strangest objects in the universe? The universe is vast beyond ordinary imagination. It stretches across distances so great that light itself, traveling faster than anything else we know, can spend millions or even billions of years quietly crossing the darkness between distant places. Within this immense expanse, countless stars shine softly in the distance. Galaxies drift in graceful spirals and clusters, slowly moving through space over spans of time far longer than a human lifetime. And among these stars and galaxies, the universe contains objects that behave in ways very different from what we experience here on Earth. Not because they are chaotic or unpredictable, but simply because the laws of physics allow many different possibilities. When scientists describe certain cosmic objects as strange, they are not suggesting something frightening or unnatural. The word strange simply means unfamiliar, something rare, something that exists far beyond everyday human experience. In many cases, these objects are calm and quiet parts of the universe. They simply follow the same physical rules that guide everything else around us. Gravity, motion, energy, time. These rules shape stars, galaxies, and the vast structures of the cosmos. And when conditions become very different from those on Earth, the results can look unusual from our perspective. Over many decades, astronomers have slowly uncovered some of the most remarkable objects known in nature. These discoveries did not happen all at once. They emerged gradually as telescopes improved and as our understanding of physics deepened. Each discovery added another piece to a larger picture of how the universe works. And each one revealed that the cosmos is capable of creating structures far more varied than early scientists once imagined. Some of these objects are incredibly dense, formed from the collapsed cores of ancient stars. Others drift quietly through interstellar space without a sun to orbit. Still others shape the motion of entire galaxies through the invisible pull of gravity. To someone looking up at the night sky, these objects remain hidden from direct view. Most of them are far too distant or too small to be seen clearly even with powerful telescopes. Yet through careful observation and patient study, scientists have learned how to detect them. They measure faint signals of light. They observe how nearby stars move. They analyze subtle changes in energy arriving from deep space. Through these quiet methods, the universe gradually reveals its more unusual creations, and what emerges is not a chaotic or frightening picture. Instead, it is a deeply ordered one. Every object, no matter how unfamiliar it may seem, follows the same calm laws of physics that govern everything else in the cosmos. The same gravity that keeps the moon in its steady path around Earth also shapes the motion of distant galaxies. The same atoms that form the air we breathe also exist, within stars scattered across billions of light years. The universe is complex, but it is also remarkably consistent. And when scientists encounter something that appears strange at first, it usually becomes understandable once the underlying physics is explored more carefully. In this way, the word strange becomes less about mystery and more about discovery. It reflects the moment when human understanding meets something new, something that has always existed quietly in the background of the universe, waiting to be noticed. Among the most fascinating examples of these unusual cosmic objects are neutron stars. These are the remnants of once massive stars that reach the end of their long lifetimes. For millions of years, such stars shine steadily, producing energy through nuclear reactions deep within their cores. During this long period, the outward pressure of that energy balances the inward pull of gravity. But eventually, the fuel inside the star becomes exhausted, and when that balance changes, gravity slowly begins to reshape the star. The outer layers expand and drift away, while the inner core collapses inward. Under these extraordinary conditions, matter becomes compressed to an incredible degree. Atoms themselves are squeezed so tightly that their structure begins to change. Electrons merge with protons, forming neutrons. And what remains is an object made mostly of these tiny neutral particles. The result is a neutron star. Despite containing a mass greater than our Sun, a neutron star is only about 20 kilometers across. This means that an enormous amount of matter exists within a remarkably small space. To imagine this density, it helps to consider a simple comparison. If a small teaspoon of neutron star material could somehow be brought to Earth, it would weigh billions of tons. Yet in space, this matter exists peacefully within the structure of the star itself, held together by gravity and supported by the unusual properties of neutron particles. Neutron stars are incredibly compact, but they are also very stable. Once formed, they can remain in this state for millions or even billions of years. Many neutron stars rotate slowly through space. This rotation comes from the original spin of the star that created them. As the core collapsed and became smaller, the rotation naturally sped up, much like a spinning figure skater who draws their arms inward. The result is a star that turns with steady precision. Some neutron stars rotate several times each second. Others spin more slowly, completing one rotation over several seconds. But regardless of their speed, their motion is calm and predictable. Another remarkable property of neutron stars is their magnetic field. Every star generates a magnetic field to some degree, including our own Sun. But when a massive star collapses into a neutron star, its magnetic field becomes greatly concentrated. The field lines that once stretched across a large star now occupy a much smaller region. As a result, the magnetic field becomes far stronger. Even so, this is simply another example of familiar physics operating under extreme conditions. The same electromagnetic forces studied in laboratories on Earth are responsible. The difference lies only in the scale. Many neutron stars emit narrow beams of energy from their magnetic poles. As the star rotates, these beams sweep through space like the steady motion of a lighthouse. When one of these beams happens to pass across Earth, astronomers detect a brief pulse of radio waves. These objects are known as pulsars. Their signals arrive with remarkable regularity, sometimes repeating hundreds of times per second. For astronomers, pulsars provide a valuable natural clock. Their predictable signals allow scientists to study many aspects of physics, including the behavior of gravity and the structure of space-time itself. Yet despite their unusual properties, neutron stars remain quiet objects drifting through the galaxy. They do not roar or explode. They simply exist, rotating slowly and steadily through the darkness. Over time, their rotation gradually slows. Their magnetic fields weaken, and they continue their long journey through space. The existence of neutron stars reminds us that the universe allows matter to arrange itself in many different forms that may seem unusual from a human perspective. Yet each one follows the same gentle rules that guide everything else in the cosmos. In the next part of this journey through the universe, the focus will move toward an even more specialized kind of neutron star, a rare variation known as a magnetar. Like neutron stars, magnetars are the remnants of massive stars that completed their life cycles long ago. But within these particular objects, the magnetic field becomes even more concentrated. And while the underlying physics remains familiar, the scale of the phenomenon grows even more remarkable. Still, like all objects in the universe, magnetars remain quiet participants in the slow and peaceful unfolding of cosmic time. Their presence simply reflects another possibility allowed by the laws of nature. Another example of how diverse the universe can be when matter, gravity, and energy interact across immense distances and vast spans of time. And as we continue exploring these unusual objects, the overall picture remains calm and reassuring. The universe is not chaotic. It is simply vast. Within that vastness, countless forms of matter exist quietly, each following the same steady principles that have shaped the cosmos since its earliest moments. Magnetars are a special kind of neutron star. They begin their existence in the same quiet way that neutron stars do, formed from the collapsed core of a massive star that has reached the end of its long life. After millions of years of shining, the star's inner balance slowly changes, and gravity gently gathers the remaining matter inward. What remains is a compact star, made almost entirely of neutrons, small in size, yet containing an immense amount of matter. Among these already unusual stars, a few develop magnetic fields that are stronger than anything else known in the universe. These are the objects scientists call magnetars. The name simply reflects their most distinctive property. Their magnetic fields are extraordinarily powerful, far stronger than the magnetic fields of ordinary neutron stars. And yet, despite the scale of these fields, magnetars remain quiet objects drifting through space, following the same calm laws of physics as everything else. To understand why magnetars are so unique, it helps to think about magnetic fields in a familiar way. Here on Earth, a small magnet can influence tiny pieces of metal placed nearby. The magnet does not move the metal by touching it directly. Instead, it creates an invisible field around itself, and that field gently guides the motion of certain materials. The Earth itself has a magnetic field as well. It surrounds the planet and extends far into space, quietly shaping the paths of charged particles arriving from the sun. Magnetic fields are simply another part of the natural behavior of matter and energy. When stars form, they also carry magnetic fields within them. These fields move and shift slowly as the star rotates and evolves over millions of years. But when a massive star collapses into a neutron star, something remarkable happens. The original star may have been hundreds of thousands of kilometers wide. When its core collapses, all of that matter is compressed into a sphere only about 20 kilometers across. The magnetic field that once stretched across the large star is now squeezed into a much smaller region. Just as squeezing a spring makes it stronger, compressing a magnetic field makes it more intense. In most neutron stars, this effect already produces an extremely strong magnetic field. But in a magnetar, the field becomes even more concentrated. Scientists believe that during the collapse of the original star, the movement of matter inside the forming neutron star may amplify the magnetic field even further. The rotation of the star, combined with the motion of its dense interior, may strengthen the field until it reaches levels rarely seen elsewhere in the cosmos. The result is a star whose magnetic influence extends far into space around it. Yet the magnetar itself remains very small. Like other neutron stars, it is only about the size of a city. Within that small sphere, however, an enormous amount of mass is contained, and the magnetic field surrounding it is incredibly strong. Despite these unusual conditions, magnetars are still governed by the same familiar forces studied in physics. Gravity keeps their structure intact. Electromagnetism shapes the behavior of their magnetic fields, and over time, their rotation slowly evolves, just as it does for other neutron stars. Many magnetars rotate more slowly than typical neutron stars. Some complete a full rotation every few seconds. This may sound fast compared to everyday motion on Earth, but in cosmic terms it is relatively gentle. As they rotate, their magnetic fields remain anchored within the star's dense interior. These fields extend outward into space, forming graceful patterns of invisible lines surrounding the magnetar. Occasionally, the intense magnetic field may shift slightly as the structure of the star slowly adjusts. When this happens, the surface of the magnetar may change by a tiny amount. Scientists sometimes describe these changes as starquakes, though the term is simply a convenient comparison to the way the Earth's crust can shift during an earthquake. In reality, the processes involved are very different. The dense surface of a neutron star behaves more like a solid lattice of particles under extreme pressure. When the magnetic field slowly rearranges itself, the surface may adjust as well. These adjustments release small bursts of energy that travel outward through space, Astronomers detect these signals as gentle flashes of radiation, usually in the form of X-rays or gamma rays. From a great distance, these signals appear as brief pulses of energy arriving at Earth. To scientists observing them, these signals are valuable sources of information. They help reveal how magnetars behave and how their powerful magnetic fields evolve over time. Yet even these bursts are simply natural processes unfolding according to the laws of physics. Magnetars are not chaotic objects. They are quiet participants in the long story of stellar evolution. Most magnetars are found within our own galaxy, the Milky Way. They are relatively rare compared to ordinary neutron stars. Astronomers have identified only a few dozen confirmed examples so far. But given the vast size of our galaxy, it is likely that many more exist, waiting to be discovered. Each magnetar drifts slowly through space, often far from the location where its original star once formed. Over millions of years, their rotation gradually slows. Their magnetic fields slowly weaken, and their activity becomes quieter and quieter. Eventually, a magnetar may become difficult to distinguish from an ordinary neutron star. The powerful magnetic field that once defined it slowly fades, leaving behind a dense stellar remnant that continues its quiet journey through the galaxy. In this way, magnetars represent a temporary stage in the life of some neutron stars, a stage where the magnetic field becomes unusually strong for a period of time before gradually relaxing back toward a more typical state. When astronomers study magnetars, they gain insight into how matter behaves under extraordinary conditions. The interior of a neutron star is one of the most extreme environments known in the universe. The pressure is immense, the density is enormous, and the magnetic field surrounding a magnetar adds another layer of complexity to the picture. By observing the signals magnetars send across space, scientists can test theories about how particles interact under such conditions. These observations help refine our understanding of fundamental physics. They also remind us that the universe contains environments far different from anything found on Earth. Yet even in these unfamiliar places, the same physical principles still apply. Gravity still shapes the motion of matter. Electromagnetism still governs magnetic fields. Energy still moves and transforms according to consistent laws. The universe may contain objects that appear strange at first glance, but they remain part of a larger, orderly system. Magnetars are a beautiful example of this idea. They demonstrate how extreme conditions can produce remarkable results while still following the quiet structure of physics. Far from being chaotic, magnetars are elegant natural laboratories. They allow scientists to observe how the universe behaves when matter becomes extraordinarily dense and magnetic fields become exceptionally strong. And yet, when viewed from the vast distances of space, a magnetar is simply another small star drifting through the galaxy. Its light is faint. Its presence is subtle. It rotates slowly in the darkness, surrounded by an invisible magnetic field that stretches quietly outward. Across millions of years, it continues its calm existence. Eventually, its magnetic strength fades, its rotation slows further, and it becomes one more quiet, stellar remnant moving gently through the Milky Way. In the immense scale of cosmic time, magnetars are brief chapters in the life stories of stars. Yet during their existence, they offer scientists a glimpse into some of the most fascinating conditions nature can create. And as we continue exploring the universe's unusual objects, another kind of cosmic structure comes into view, one that is perhaps the most widely known, yet also one of the most misunderstood. These are black holes, objects where gravity becomes so strong that space and time themselves are shaped in unusual ways. Despite their reputation, black holes are not destructive monsters hiding in space. They are simply regions where matter has gathered so densely that gravity becomes extremely powerful. Like neutron stars and magnetars, they arise naturally from the life cycles of stars. And like everything else in the universe, they follow the same quiet laws of physics that guide the motion of galaxies. and the gentle glow of distant stars. In the next part of this exploration, the calm structure of black holes will come into focus. Their shape, their boundaries, and the way gravity quietly organizes space around them. Black holes are among the most widely known objects in astronomy. Their name often creates the impression of something mysterious or dramatic, yet in reality, they are calm structures formed through natural physical processes. They are not objects in the usual sense of a solid surface or visible sphere. Instead, a black hole is a region of space where gravity has become extremely strong. This strength of gravity comes from matter gathering into a very small volume. When enough mass is compressed into a sufficiently compact region, the pull of gravity grows stronger and stronger. Eventually, it becomes so strong that even light, which normally travels freely across the universe, cannot easily escape from the region surrounding that mass. This condition defines what scientists call a black hole. The idea of black holes first appeared not through observation, but through mathematics. In the early 20th century, physicists began exploring the implications of Albert Einstein's theory of general relativity. This theory describes gravity not as a simple force, but as the curvature of space and time caused by mass and energy. Objects such as stars and planets create gentle curves in the fabric of space-time. These curves guide the motion of nearby objects, producing what we perceive as gravity. When scientists explored the equations of general relativity under extreme conditions, they found that space-time could become curved to an extraordinary degree. If enough mass were concentrated in a small region, the curvature would deepen so much that a boundary would form. This boundary is known as the event horizon. The event horizon marks the distance from the center of the black hole, where gravity becomes strong enough that light cannot travel outward fast enough to escape. Inside this boundary, all paths through space-time lead inward. From the outside, however, the event horizon behaves as a quiet and invisible surface in space. Nothing unusual happens if an object simply passes nearby. The gravitational pull of a black hole behaves much like the gravity of any other object with the same mass. If our Sun were somehow replaced by a black hole of equal mass, the Earth would continue to orbit in exactly the same way it does today. The difference would simply be that the source of gravity would be far smaller and invisible. Black holes most commonly form when very massive stars reach the end of their lifetimes. For millions of years, a large star shines by producing energy through nuclear reactions in its core. These reactions create an outward pressure that balances the inward pull of gravity. But once the star's fuel is exhausted, that balance gradually changes. Gravity slowly gathers the remaining matter inward, compressing the core more and more. In some cases, the core becomes a neutron star, as described earlier. But if the star is massive enough, gravity continues compressing the matter beyond that stage. The core collapses further and further until the region becomes small enough that a black hole forms. From the outside, this process eventually settles into a stable structure, a black hole with a surrounding region of curved space-time. Once formed, a black hole can exist quietly for extremely long periods of time. It does not wander through space, searching for objects to consume. Instead, it simply remains where it formed, influencing nearby matter through gravity. Gas, dust, or stars that happen to pass close enough may begin orbiting around the black hole. When this occurs, the material often forms a thin, rotating disk around the black hole, known as an accretion disk. Within this disk, particles move in graceful spirals, slowly drifting inward over time. As they move closer to the center, the energy of their motion may produce light and other forms of radiation. Astronomers often detect black holes by observing this surrounding disk of glowing material. In many galaxies, including our own Milky Way, there are black holes far more massive than those formed from individual stars. These are known as supermassive black holes. They sit quietly at the centers of galaxies and can contain the mass of millions or even billions of suns. The one at the center of the Milky Way is known as Sagittarius A star. Despite its enormous mass, it occupies a region smaller than our solar system. Stars near the center of our galaxy orbit around it in smooth, predictable paths, guided by gravity. These stars have been observed carefully for decades, and their motion reveals the presence of the invisible mass at the center. Supermassive black holes appear to be common throughout the universe. Nearly every large galaxy studied so far seems to contain one at its center. Yet even these immense objects remain calm features of cosmic structure. They slowly influence the motion of stars and gas in their surroundings, shaping the long-term evolution of their galaxies. For many years, black holes remained purely theoretical objects, but in recent decades, new technologies have allowed scientists to observe them more directly. One of the most remarkable achievements came in 2019, when astronomers working with the Event Horizon Telescope produced the first image of a black hole's shadow. This image showed a bright ring of light surrounding a dark central region. The dark region corresponds to the shadow created by the black hole's event horizon. The surrounding ring forms from glowing gas orbiting nearby. This image provided powerful confirmation of decades of theoretical predictions. It showed that black holes behave exactly as the equations of general relativity describe. In the years since then, further observations have continued refining our understanding. Scientists now study how black holes interact with nearby matter, how they grow over time, and how they influence the galaxies around them. One particularly fascinating discovery involves the way black holes can merge. When two black holes orbit one another, they gradually spiral closer together over millions of years. Eventually, they combine into a single, larger black hole. During this process, ripples spread outward through space-time itself. These ripples are known as gravitational waves. For the first time in 2015, scientists detected gravitational waves using instruments called LIGO detectors. The signals came from two black holes merging more than 1 billion light-years away. These tiny vibrations in space-time confirmed another prediction of Einstein's theory. Yet even these powerful events occur silently across vast cosmic distances. By the time the gravitational waves reach Earth, they are incredibly faint. Sensitive instruments measure them with extraordinary precision. Black holes may seem unusual, but they are simply another natural outcome of gravity acting over immense scales. They follow the same rules that guide the formation of stars, planets, and galaxies. Their behavior can be described through the same physical principles that govern the rest of the universe. In this way, black holes remind us that the cosmos contains many environments far beyond our everyday experience. Yet these environments remain orderly and understandable. They are not chaotic or mysterious once their underlying physics becomes clear. Far from being frightening, black holes are elegant examples of how nature organizes matter and energy under extreme conditions. They are quiet structures woven into the fabric of the universe, and as astronomers continue observing them, they reveal deeper insights into how space and time themselves behave. Beyond these remarkable regions of intense gravity, the universe also contains objects that are unusual for a very different reason. Not because they are dense or powerful, but because they travel alone. These objects are known as rogue planets. Unlike Earth or Jupiter, rogue planets do not orbit a star. They drift quietly through interstellar space, moving slowly through the darkness between the stars. Their journeys are long and silent, and they represent yet another example of the many surprising forms that matter can take in the universe. Rogue planets are among the quiet travelers of the universe. Most of the planets we know exist within planetary systems. They orbit stars, moving in steady paths shaped by gravity. In our own solar system, Earth and the other planets circle the Sun in calm, predictable motion, completing their orbits year after year. This pattern is common throughout the galaxy. Around many stars, astronomers have discovered planets of many sizes, large gas giants, rocky worlds, and icy bodies drifting far from the warmth of their suns. Yet not every planet remains within such a system. Some planets travel alone. These solitary worlds are known as rogue planets. They drift through the vast spaces between stars, moving quietly through the galaxy without orbiting any sun. Their journeys can last for millions or even billions of years. From a distance, a rogue planet is very difficult to see. Without a nearby star to illuminate it, the planet reflects very little light. Most of the time, it remains almost completely dark, blending into the deep background of space. Yet even in darkness, a rogue planet still exists as a complete world. It has its own gravity, its own surface or atmosphere, its own long and silent path through the galaxy. Scientists believe that many rogue planets once formed within ordinary planetary systems. During the early stages of planet formation, young solar systems can be busy and crowded environments. Gas and dust swirl around newly formed stars, gradually clumping together into planets. As these young planets settle into their orbits, gravity gently guides their motion. Sometimes, however, the gravitational interactions between multiple planets can shift their paths. Over long periods of time, these interactions may slowly change the shape of an orbit. Occasionally, one planet may receive enough gravitational influence from its neighbors to be pushed outward. If this outward motion continues, the planet may eventually escape the gravitational pull of its star. Once it crosses that boundary, it begins a new life as a rogue planet. It drifts freely through interstellar space. Another possibility is that rogue planets can form independently within clouds of gas and dust, similar to the way stars themselves form. In these cases, a small clump of material may gather enough mass to become a planet-sized object, but not enough to ignite the nuclear reactions that power stars. Such objects remain cool and dim, wandering quietly through the galaxy. Because rogue planets emit very little light, astronomers often detect them using indirect methods. One of the most fascinating techniques is called gravitational microlensing. This effect occurs when a rogue planet passes in front of a distant star from our point of view on Earth. As the planet moves across the line of sight, its gravity bends the light coming from the distant star behind it. The star appears to brighten slightly for a short time. This gentle increase in brightness reveals the presence of the otherwise invisible planet. Using this method, astronomers have discovered that rogue planets may be surprisingly common. Some estimates suggest that there could be billions of them drifting through the Milky Way. In fact, there may be as many rogue planets as there are stars. These worlds vary greatly in size. Some are small rocky planets similar to Earth or Mars. Others are large gas giants resembling Jupiter. Many of them likely formed in distant solar systems long ago, before being gradually pushed outward into interstellar space. Once a planet becomes a rogue, its environment changes dramatically. Without the warmth of a nearby star, the surface of a rogue planet becomes extremely cold. Any oceans that once existed on the surface would likely freeze over time. Atmospheres may slowly thin or condense into frozen layers on the surface. Yet deep within some rogue planets, warmth may still exist. Inside large planets, the natural decay of radioactive elements can produce heat. Additionally, the pressure deep within the interior of a massive planet may keep certain regions warm for very long periods of time. In theory, beneath thick layers of ice, some rogue planets might even contain hidden oceans kept liquid by internal heat. These possibilities remain subjects of ongoing scientific study. For now, the most important aspect of rogue planets is simply their quiet existence. They move slowly through the galaxy, guided only by gravity. Their paths may take them near distant stars from time to time, though most spend long stretches of time traveling through the dark spaces between stellar systems. Despite the isolation of these worlds, their journeys are not chaotic. They follow predictable paths through the gravitational landscape of the galaxy. Just as stars orbit the center of the Milky Way, Rogue planets also move along similar broad paths, carried by the gentle pull of the galaxy's mass. In this way, they remain part of the same cosmic structure as everything else. They are simply less visible travelers. The idea of a planet wandering through interstellar space might seem unusual at first, yet once again, it is simply another possibility allowed by the laws of physics. Gravity shapes the formation of planetary systems, and sometimes gravity also rearranges them. Over immense spans of time, small changes can lead to large outcomes. A planet that once circled a star may gradually drift away, beginning a new journey through the wider galaxy. This quiet transition reflects the long timescales over which cosmic events unfold. Millions of years pass as planets slowly adjust their paths. Billions of years pass as galaxies continue their slow rotation through space. Against this vast background of time, rogue planets are simply another example of the universe's diversity. They are silent worlds moving through the darkness. Each one carries the history of its formation, the memory of its original system, and the quiet motion that now guides its path. When astronomers search for rogue planets, they do so not because these objects are dramatic or unusual in a threatening way. Instead, they represent another piece of the larger puzzle of how planetary systems evolve. By studying them, scientists learn more about how planets form, how gravitational interactions shape solar systems, and how common different types of worlds may be throughout the galaxy. The discovery of rogue planets also expands our sense of what a planetary environment can be. Some worlds orbit warm stars, others orbit dim red dwarfs, and some travel alone through interstellar space. Each one exists quietly within the same universe. Beyond these wandering planets, the universe also contains structures that are unusual, not because of their density or motion, but because of their emptiness. Vast regions where galaxies become rare, expanses where the distance between cosmic structures grows larger and larger. These regions are known as cosmic voids. They are some of the largest structures in the universe, and yet they are defined by how little they contain. The next part of this exploration, the focus will shift to these immense quiet spaces between galaxy clusters, places where the universe becomes calm and open, stretching across distances that are almost impossible to imagine. Within these vast voids, the silence of space becomes even deeper, and the structure of the cosmos reveals itself on the grandest possible scale. Cosmic voids are among the largest structures known in the universe, though they are defined not by what they contain, but by what they gently lack. When astronomers map the positions of galaxies across the observable universe, they do not find them scattered evenly through space. Instead, galaxies form delicate patterns that stretch across unimaginable distances. These patterns resemble vast networks of filaments and clusters, where galaxies gather together in long threads and enormous groups. Between these threads lie immense open regions where very few galaxies exist. These wide, quiet spaces are known as cosmic voids. A cosmic void can stretch across tens or even hundreds of millions of light years. Within such a region, galaxies are sparse and distant from one another. Some voids contain only a handful of small galaxies drifting slowly through the darkness. From a distance, the structure of the universe begins to resemble a soft web or foam, where bright clusters of galaxies form the edges and boundaries, while the interiors remain largely empty. This pattern did not appear suddenly. It formed gradually over billions of years as gravity shaped the distribution of matter across the universe. In the early universe, shortly after the cosmos began expanding, matter was spread out almost evenly. Tiny variations in density existed, regions where slightly more matter was present than in surrounding areas. Over time, gravity slowly amplified these small differences. Where slightly more matter existed, gravity gently pulled additional material inward. Galaxies began to gather together, forming clusters and long strands of cosmic structure. Where slightly less matter existed, the opposite happened. Matter gradually drifted away from those regions, leaving behind larger and larger empty spaces. These expanding gaps eventually became the cosmic voids we observe today. Despite the name, cosmic voids are not completely empty. A few faint galaxies can still be found drifting within them, and extremely thin traces of gas may remain scattered through the space. But compared with the crowded regions of galaxy clusters, voids are remarkably quiet places. The distances between galaxies inside a void can be enormous. A galaxy within a void might travel tens of millions of light-years before encountering another large galaxy. Yet even within these immense expanses, the same gentle laws of physics continue to operate. Gravity still shapes the slow motion of galaxies. Light still travels through space across immense distances. Time continues unfolding at its steady pace. The difference lies only in the scale of separation. In a dense galaxy cluster, thousands of galaxies may occupy a relatively small region of space. Their gravity gently influences one another, guiding their motion in complex but predictable ways. Inside a cosmic void, that influence becomes much weaker. With fewer nearby galaxies, each one moves more freely through the quiet emptiness. Astronomers study cosmic voids carefully because they provide valuable insight into how the universe evolved. By examining the size and distribution of voids, scientists can test their understanding of how matter and gravity shape the large-scale structure of the cosmos. Voids act almost like natural laboratories. Because they contain so little matter, the physical processes within them can sometimes be easier to study than in crowded galaxy clusters. For example, the few galaxies that form within voids often evolve in relatively isolated conditions. Without frequent interactions with neighboring galaxies, they can develop slowly and peacefully over billions of years. Studying these galaxies helps astronomers understand how galaxies behave when left largely undisturbed. Cosmic voids also help scientists investigate one of the most subtle forces shaping the universe: dark energy. Dark energy is the name given to the mysterious effect causing the expansion of the universe to gradually accelerate. Although dark energy cannot be observed directly, its influence becomes clearer when astronomers study the large-scale structure of the cosmos. Voids slowly grow larger over time as galaxies drift toward the denser filaments and clusters surrounding them. By measuring how quickly voids expand, scientists gain clues about how dark energy affects the expansion of space itself. Yet even when studied through these advanced ideas, cosmic voids remain quiet places. They are not violent or chaotic environments. Instead, they represent the calmest regions of the universe. If one could imagine traveling through a cosmic void, the experience would be defined by vast stillness. The nearest galaxies might appear only as faint points of light, scattered widely across the darkness. Between them would lie enormous stretches of open space. These expanses remind us that the universe is not filled uniformly with matter. Much of its volume is made up of these quiet regions where galaxies are rare and distances are immense. And yet, these voids are not separate from the rest of the universe. They are part of the same grand structure. The same cosmic web that forms clusters and filaments also defines the boundaries of voids. Together, these structures shape the large-scale pattern of the cosmos. Over billions of years, this pattern continues to evolve slowly. Galaxies drift along the filaments toward denser clusters. Voids gradually expand as matter moves away from their centers. The entire process unfolds gently across cosmic time. Nothing about it is sudden. Nothing about it is chaotic. It is simply the steady motion of matter responding to gravity across enormous distances. When astronomers map these structures using powerful telescopes and large sky surveys, the result is one of the most beautiful images of the universe ever revealed. Millions of galaxies appear as tiny, glowing points connected by delicate strands of structure. Between them stretch vast, dark regions where almost nothing can be seen. These maps show the universe not as a random scatter of objects, but as an organized and evolving network. Cosmic voids are essential parts of that network. They provide the open spaces that allow the cosmic web to take shape. And they remind us that emptiness itself can play an important role in the structure of the universe. In the immense scale of cosmic distances, both matter and emptiness work together to shape the universe we observe. Clusters of galaxies glow with the light of billions of stars. Filaments stretch like gentle bridges between them. And between those bridges lie the quiet, open voids. All of these structures follow the same simple laws. Gravity slowly gathers matter. Space continues to expand. Time carries everything forward. When we step back and view the universe as a whole, these unusual objects, neutron stars, magnetars, black holes, rogue planets, and cosmic voids, begin to feel less mysterious. Each one is simply another expression of the same underlying physics. Different conditions lead to different results. Dense stars collapse into neutron stars. Magnetic fields concentrate to create magnetars. Gravity shapes regions of space into black holes. Planets drift away from their stars and become rogues. Matter gathers along filaments, leaving behind vast cosmic voids. Yet none of these outcomes are chaotic or unnatural. They are simply the universe exploring the possibilities allowed by its own physical laws. And when viewed with patience and curiosity, these objects reveal a cosmos that is deeply ordered and quietly beautiful. As this exploration gently comes toward its close, the perspective begins to widen once more. Instead of focusing on individual objects, attention returns to the universe as a whole. A vast place containing countless structures, each one following the same quiet principles that have guided the cosmos since its earliest moments. The universe may contain objects that appear unfamiliar at first, but with time, observation, and understanding, even the strangest objects become part of a larger, peaceful picture. Across the vastness of the universe, objects of many kinds exist quietly within the same cosmic landscape. Some are dense and compact, like neutron stars and magnetars. Others shape the motion of space around them, like black holes. Some travel alone through the darkness, like rogue planets. And some are defined by their remarkable openness, like the immense cosmic voids that stretch between clusters of galaxies. When these objects are first described, they can sound unusual. Their properties often exist far beyond the range of everyday human experience. Matter compressed to extraordinary densities, magnetic fields stronger than anything found on Earth, regions where gravity bends the path of light, planets moving through space without a star to guide their orbit. Yet once we look more closely, these objects reveal something deeply reassuring. They are not chaotic or unpredictable. They simply reflect the many possibilities allowed by the quiet laws of physics. The same principles that govern the motion of a falling leaf on Earth also apply, in different ways, to the motion of galaxies across the universe. Gravity, energy, motion, and time operate everywhere, shaping matter into forms both familiar and unfamiliar. Over centuries of observation, human understanding of the cosmos has gradually grown. Early astronomers looked up at the night sky and saw only small points of light scattered across darkness. Those distant lights seemed simple and unchanging. But as telescopes improved and scientific ideas developed, a deeper picture slowly emerged. Each of those points of light became a star, often surrounded by planets. Groups of stars formed galaxies. Galaxies gathered into clusters and filaments, stretching across enormous distances. And within these structures, new kinds of objects appeared, objects that revealed how flexible the universe could be when matter and gravity interact over long periods of time. The discovery of neutron stars, magnetars, black holes, rogue planets, and cosmic voids did not replace the earlier picture of the universe. Instead, these discoveries expanded it. They showed that the universe contains far more variety than anyone once imagined. Yet this variety exists within a consistent and understandable framework. The same equations of physics describe the interior of a neutron star and the motion of a drifting planet. The same gravitational laws shape both the orbit of the Earth and the slow gathering of galaxies into clusters. Even the most unusual objects remain part of a unified cosmic system. In many ways, the strangeness of these objects comes only from the limits of human perspective. Our everyday experience is shaped by the conditions of Earth. Moderate gravity, familiar temperatures, and matter arranged in forms that are comfortable for life. But the universe is far larger than any single environment. Across billions of galaxies, matter exists under countless conditions. Some regions are hot and bright. Others are cold and quiet. Some are crowded with stars. Others stretch into immense emptiness. When matter and energy interact across such a wide range of conditions, new structures naturally appear. Dense stellar remnants, wandering planets, regions where gravity curves space itself, immense voids where galaxies become rare. Each of these objects reflects a different balance of forces. Gravity gathering matter inward, energy pushing outward, magnetic fields shaping invisible patterns, seen it through space. Over billions of years, these forces have quietly sculpted the universe into the vast structure we observe today. And throughout that immense process, everything unfolds gradually. Stars take millions of years to form. Galaxies evolve across billions of years. Even the largest cosmic structures grow slowly over time. Nothing about the universe moves in haste. Instead, it unfolds with extraordinary patience. This slow pace allows astronomers to observe and understand these processes step by step. New telescopes gather faint light that has traveled for millions of years before reaching Earth. Sensitive detectors measure tiny signals arriving from distant objects. Computer simulations help scientists explore how matter moves and changes over cosmic time. Through these methods, the universe gradually becomes clearer. Objects that once seemed mysterious become understandable. Patterns that once appeared random reveal their underlying order. And the strange objects, scattered across the cosmos, become part of a larger story. A story of how matter behaves when gravity and energy shape it across enormous distances and vast spans of time. This understanding does not remove the wonder of the universe. If anything, it deepens it. Knowing how neutron stars form makes them even more remarkable. Understanding the structure of black holes reveals the elegance of space-time itself. Observing rogue planets drifting through the galaxy highlights the many paths planetary systems can follow. And mapping cosmic voids shows just how vast and open the universe truly is. Each discovery expands the sense of scale in which the cosmos exists. Billions of stars within a single galaxy. Billions of galaxies across the observable universe. Distances so great that light itself requires immense stretches of time to cross them. Within this immense stage, the unusual objects explored here are simply part of the natural diversity of cosmic structure. They do not disrupt the universe. They help define it. They reveal how flexible and creative the laws of physics can be when allowed to operate across immense scales. And perhaps, most importantly, they remind us that the universe is not limited to the conditions we experience on Earth. There are many ways for matter to exist, many ways for gravity to shape structure, many ways for energy to move and transform. All of these possibilities unfold quietly across the cosmos, guided by the same steady principles. As the exploration of these strange objects gently comes to a close, the wider picture of the universe begins to feel calm and balanced. Stars shine steadily across distant galaxies. Planets orbit their suns. Some planets wander alone. Some stars collapse into dense remnants. Vast regions of space remain open and silent. All of it exists together within the same cosmic system. Nothing is out of place. Nothing is separate from the rest. Each object, no matter how unusual it may appear, is simply following the quiet, path set by the laws of nature. And across the immense span of cosmic time, those laws continue shaping the universe in slow, graceful ways. Galaxies drift through space, stars are born and fade, new planets form within clouds of dust and gas. And far from any star, silent worlds continue their gentle journeys through the darkness. When viewed from this wider perspective, the universe feels less like a place of mystery and more like a vast and patient landscape, a place where countless structures exist peacefully together, some dense, some distant, some bright, some nearly invisible, all part of the same unfolding story. A story written not in sudden events, but in quiet processes that continue for billions of years. The strange objects within the universe are simply moments within that story, natural outcomes of gravity, motion, and time. They do not break the harmony of the cosmos. They are expressions of it. And as the universe continues its slow expansion, these objects will remain scattered across its vast distances. Neutron stars rotating quietly, magnetars slowly releasing their magnetic energy, black holes shaping space around them, rogue planets wandering through interstellar darkness, cosmic voids stretching between the great filaments of galaxies. Together they form a universe that is both complex and calm, a universe where even the strangest objects follow gentle and consistent rules. And within that calm structure, the cosmos continues its long and peaceful journey through time. As this quiet journey through the universe begins to come to rest, the many unusual objects we have explored start to settle gently into a single, peaceful picture. Neutron stars, magnetars, black holes, rogue planets, and the vast cosmic voids between galaxies. At first, each of these may seem strange when described on its own. Their scales are immense. Their environments are far beyond anything experienced in everyday life. Matter becomes denser than we can easily imagine. Gravity bends the structure of space itself. Entire planets drift alone through darkness. Enormous regions of the universe stretch outward with almost nothing inside them. Yet when we look at them slowly and calmly, something reassuring becomes clear. None of these objects exist outside the natural order of the universe. Each one simply follows the same quiet laws of physics. Gravity gently gathers matter together. Energy moves and transforms. Space expands slowly over time. From these simple principles, the universe allows many different forms to appear. Some stars collapse into dense neutron stars that rotate softly in the darkness. A few of those stars briefly become magnetars, carrying magnetic fields of extraordinary strength before gradually settling into quieter states. In other cases, gravity gathers matter so tightly that a black hole forms, shaping the space around it while remaining almost completely invisible. Planets that once circled distant stars may drift away and begin long solitary journeys between stellar systems. And across the largest scales of all, galaxies gather into delicate filaments while vast cosmic voids open quietly between them. None of these structures rush. None of them appear suddenly. They unfold across immense stretches of time. Millions of years. Billions of years. The universe moves with extraordinary patience. Stars form slowly within drifting clouds of gas and dust. Galaxies grow as gravity gently gathers matter inward. Even the largest cosmic patterns evolve gradually, almost imperceptibly from one human lifetime to the next. Seen from this calm perspective, the strange objects of the universe begin to feel less like mysteries and more like natural expressions of possibility. They show what matter can become when gravity, energy, and time interact across enormous distances. They reveal how flexible the universe can be, while still remaining orderly and balanced. The cosmos is not a chaotic place. It is a deeply structured one. Every star, every planet, every galaxy and every quiet region of empty space follows the same gentle framework. Even the most unfamiliar objects are simply variations within that framework. And within this vast cosmic landscape, the night sky becomes something even more meaningful. Each faint point of light represents a star with its own history. Some stars are young and newly formed. Others have already completed their long lifetimes. Around many of them, planets circle quietly. Far beyond them, entire galaxies drift through space. Between those galaxies lie the immense voids where the universe opens into silence. All of it exists together in one vast, connected system. A system shaped by simple physical laws that have guided the universe since its earliest moments. When we reflect on these ideas slowly, the universe begins to feel less distant, not because its size becomes smaller, but because its structure becomes understandable. The strange objects scattered across the cosmos are not interruptions to the harmony of the universe. They are part of that harmony. They are reminders that nature can create many different forms while still following the same calm rules. And as the universe continues expanding, these objects will remain part of its quiet rhythm. Neutron stars will continue their slow rotations. Magnetars will gradually soften their magnetic strength. Black holes will rest silently within galaxies. Rogue planets will drift patiently through interstellar darkness. Cosmic voids will stretch between the great webs of galaxies. Together, they form a universe that is vast, varied, and deeply peaceful. A universe where even the strangest objects are simply expressions of the same quiet physics that shapes everything else. And across the immense flow of cosmic time, this calm structure continues. Galaxies turning slowly, stars shining softly, planets traveling through space. And far beyond the reach of any single world, the universe unfolds with patience, balance, and quiet beauty.